Then I'm ready to just modify the board to make the changes. Not sure how easy that is going to be, but I have to do them. And now the new board I have ordered, I don't bother solder it up because it has the fault also. I think we'll make a cut here. Because this is the output of the isolator. To change these two, to flip them, we'll just make a cut here and then run wires from here to here and here to here. Should do the trick. So in this part of the project it's time to introduce the AC voltage. And the display and the microcontroller, like the whole add-on thing, is run by AC. Then it's rectified here and smoothed with that big capacitor there. And you can see it works. So what I've done is I've taken, this is my old Saver anyway, so it's the Commodore power supply, taken out the AC part, in on the AC pins, and you can see it runs it just fine. And this is the scope image, so if I switch it off you can see it drops. So we're on 5 volts, so that's great. So now we can continue testing. The nice thing now is that I can use external power supply. I haven't tried this, maybe it blows up. Because now I have 5 volt on that regulator all the time. So let me demonstrate what's going on here. The 9 volt AC comes in here and we have 5 volts, so let me just turn on one at a time. Bringing in 5 volt. I can go to over voltage, the output goes off. See the LED there, that's the output. Going back down, it comes on. Now the add-on board is dead. So now if I bring in the C64 power supply, then the add-on board turns on. Look, it starts to control the output. And the add-on board is isolated from this 5 volt output and input. It controls this. So basically it turns on an LED and then a transistor on the other end, phototransistor, turns on. So that's the isolation part. So now what have we checked already? We have checked this one, this one. We know that this one works. I'm reading out the registers here. Config current after calibration has been calculated. So the INA actually does that for us. I'm not doing any calculations there. Just reading out. This is the shunt voltage. And this is calibration value. Something like that. I don't know, it's something else. I have to check. Now I had the wrong shunt resistor connected. So I had 1 ohm because I didn't have the 0.1 yet, as you can see in the picture. But now that I have 0.1 and we are moving, let's say, if I bring in the LED again, or the 21 milliamps. So if you divide this number by 100, you get 2.5 or 2.6. Let's say 2.6. So that's millivolts. So actually we're measuring 2.5 millivolts over the shunt. And if you divide that by the shunt, which is 0.1, you get 25 millivolts, or 26. And we have 21 here. So we also have 21 here. That is because I set the calibration register. I've taken some measurements of the 9V AC and the rectified value, and then the 5V after a regulator, just to see what the ripple looks like. So this is 220 microfarad, but it's actually 100. There's not much room for larger. And this side is powering the OLED, as well as this part and this one and this one. So, and there's some pull downs here and some current, but that's very little. Like microamps. Might be a little bit higher here though, so, but not much. It's under a milliamps anyway. Here we have 5 millivolts per division, and you can see we have almost 15 volts peak to peak. So this is an unloaded power supply. You can also see the divided voltage here, which is much smaller, and it's 2.5 volts amplitude. And I'll show you why, because in the next image you can see it shifts up. This one stays the same, of course, but this one is now between 0 and 5 volts, and that's because of the microcontroller. So the microcontroller can only take voltages between 0 and 5 volts. And here we go. So here you saw the divided voltage. We run it through a capacitor to shift the DC level, and these two just keep the DC at between 5 and 0, so that's 2.5 volts. So we can measure up to 2.5 volts after the division here. So we need to put a addon here, I think. Well, I have to check that because this is ADC inputs. This is not an ADC, is it? I have to check this one. Okay, so my computer just froze, so just look at something else instead. So we have rectification here and 5 volts. So let's have a look at the scope, see what that looks like. This is the measurement. So we have 5, 10, 15 volts. And we have a lot of ripple here, but as long as this value, let's see here, is not below that, or the lowest possible is not below there, it should work okay, but it's a bit much. This is actually the ripple is worse when you shut off the output, because then you have to drive the upscoupler. And yeah, and this is when the OLED had all the white pixels illuminated. And the reason being because this is 100 microfarad. I don't think I can get any larger because it doesn't fit. So instead of increasing the capacitance here, we can move this. Alright, so the sense vac is going in on the wrong place. Let's see about the sense accuracy. This comes from this guy over here. ACS712 is basically measuring the current going through here, through a Hall effect sensor. So when there's no current, there's 2.5 volts out here. Yes, that was an interesting bug there. So I'm using Git issues to collect bugs and write down bugs. So it's easier for me when it takes a long time between the PCB manufacturing and everything to check. So I have to check before I order, and I have to check other things. But then I made also a README with all the changes, and then I closed them. So let's have a look at this one. So the sense back feeds in on an ADC input, non-ADC input. So what I suggest is to swapping it with a sense back with hold. Now that creates another problem here. So if I do that, I get an analog value in on the ADC, that's fine. But then I get a digital value in on my cell. Well, it's an output anyway, so it should work, but this hold value is pulled out to ground. So the way I'm going to modify this is going to make a cut down here for the hold signal, because we're swapping this with this one. And then I'm going to cut here, and as we'll see we don't have the cut because I already have a bridge here. So, and then we're just going to jumper wire, so let's have a look. Yeah, so this is the where I'm going to cut. And here you see that sense vac over there, the bridge, I'm going to remove it. So here I'm doing the mod, and you can see it's not very pretty, but it have to do, and you can also see I haven't soldered both ends there yet, and this is what it looks like when it's finished. So yeah. So it's still working, so that's fine. And I'm gonna do that mod here. We're now looking at an older version of the PCB, so this is PCB 1.0, and here you can see we draw VEN minus, which is the power supply input, after the shunt resistor. That means this 5V section is drawing power through the shunt resistor, like this. And then we get that out on the measurements. So I've already fixed that, but not on the modification. I haven't mod the board, so I will just make a cut here and then join here. We have made a cut on the left side there, and a solder blob, and scratched the solder mask on the right side. So I'm happy with this. Yeah, so the whole deal about this was not to let the 5V section draw any power to show up on the meter, so only load on the output. So this is basically a load, so I can bring it down again. You can see it goes up. It shows twice as much amount. It's not 20 milliamps, so yeah, so something is wrong there, but we'll do that later. You can also see something else that's funny. If you watch the number here, that lower one, you see it follows the power supply. Now I have 3.3 volts in, so it's twice, look, and times 100 or something, or 1000 actually. So, and then I go to 5V, exactly there, you can see 10,000. Let's go to 6V, 12,000, go to 7V, 14, and I think I can go all the way up to, let's say, 16V. There you go. Now it will wrap around probably. No, it doesn't. It doesn't. Wow. I thought it was going to go negative or something. Now we are at 100V. I don't dare to go much further. So yeah, see, it follows. Great. That works fine. Thanks. So I was thinking, is it still working? So yeah, it is working. And can we program? Yes, we can program. So, but now we have that issue, if you can call it issue. You see this one is flashing a bit when you program, because the MISO or MOSI or whatever is connected to the same signal as controlling the output. So yeah, but it seems to be working fine. So it gets the program, and we get AVR dude done. Thank you. So when I bring in the probe over here, measure, I can't see anything on the output. So when I come to think of it, the I/O pin there is an output still in the code, so just need to switch it over. So let me try this here. I've changed it to PB1, so yeah, there it is. Great, so now it's working. And the output is switching again, so I guess that's a success. Got the output connected to the load, the one I'm using for the C64 Saver, so I can load like this. So I can switch it on, you can see it dims. And here you can see also it goes to 500 because this one is set to limit 500. So if I now bring in the 9V AC, I will turn on the microcontroller. There we go. And now I have an overcurrent feature. Look at this. Overcurrent. So the output shuts off. And the voltage is still 5V, so it says overcurrent. So let's get that again, just a bit more controlled this time. This, bring in overcurrent, there you go. And I can turn off the overcurrent, but it's stuck, it's triggered. So you see the output is not supplying more than 11 milliamps. So I have to remove power to make it go back again, as you can see. So yeah, I can try it again. There you go, so that's the new feature. So this will be configured. So the user can say how much milliamps he wants. Been programming for a while now, and this is what I have. You see AC voltage and current on the left side, and then you have DC current and voltage on the right side. On the right side they are taken from the INA. On the left side it's pure ADC from the microcontroller, 10-bit ADC. So the way I'm doing that is I have a loop. I have several loops, but I just basically find the maximum values here. So this is the formula from the datasheet. So you take Vref, which is about 5V, divide by the number of possible states, which is 1024, and then if you multiply that by the ADC value, you get the measurement. In my case, I get well, I don't get peak to peak, but I get I get a value that is current value, but this is an AC thing, so I have to sample it many times, and I will collect the highest and the lowest measured value and then display it after a while. And I also have a voltage divider to be able to measure high voltages. So when I measured 10.75, I measured after the divider 0.962, which is a factor of 11.175. You can change this formula into a new formula, which is V out equals this factor times V in though. So yeah, so and then, so what is VAC then? Well, you can take the peak to peak, which is from here to here, divided by 2, so you get from here to here. And then since you don't fill a square here, but a sign, you have to divide by root of 2 to get the RMS, or approximate RMS. So that's VAC. Now that I'll be using later. So you can see here the peak to peak, which is there. This is basically what I'm calculating now. Is Vref times ADC divided by 1024. So that's that value, or that factor, but I need this factor as well to bring it back to V out. So that's what I'm doing here, 11.175 times the ADC conversion, divide by 2, divide by the root of 2, bring it all together and get another factor, a composite factor. So, but I don't have comma or floats in my calculations, so what I do then, just move the comma 4 places, and then you get to 1,9 rounded up to 3 divided by 10 thousandths. So that's 2 operations for that factor. Now you can't. The problem with 193 divided by 10 is that you get overflow, so that doesn't work because I have 16-bit precision. So if I multiply by 193, it goes over. So what I do then, I divide it up in 2 operations, so I can multiply by 19 and get away with it. And then I can multiply by 3 and divide the result by 10 again. That will also work. So yeah, so that's what I'm doing. Value is actually 10.7 or something, so it's not that off. I might calibrate it at some time. I'm not sure how well it will look. Yeah, I will see when this get out under a load. The 11.1 there will drop. So, but that has been fun. So I've been playing around. You can see the output LED is flickering. It's flickering for every update of the screen. So I've been tweaking my loop. First, I was thinking, okay, I will update everything every 100 milliseconds or so, and if it's faster, I will put in some slack using a timer, such that every update is the same, because then I can know, for example, the difference between a long press and a short press. Then you need to have timing correct, but that slows things down if you have blocking code. So what I've done instead is that I'm not blocking. So when so what I'm displaying here is 50 milliseconds. Let me stop it. Per division. So it's about 15 milliseconds in. Let's see. Outside the loop, so to explain this program, I can just show you the code. Actually, maybe it's better that way. So it becomes a bit cryptic when you start adding timing, but as I said, I don't have any blocking code anymore, so that means that the functions that read the ADC, for example, up here, has to remember the old value, and it has to be replying with that old value until it has been polled for like 3,000 times, because then I'm certain that I've sampled this waveform so many times that I'm sure I've gotten the highest and the lowest value. So yeah, but if I was going to do that and make everything wait for it, then and I would have like 200 or 100 millisecond, because I have 2 of these, one for AC current and one for VAC. So now that doesn't work. So what I do then, I just, if you look closely, you can see that the numbers on the right side, they blip a bit much faster than the ones on the left there. So basically they are painted as often as this in a circle like this, but the values don't really update themselves before this counters timeout. So yes, I've been tweaking on that. So going back to the loop again. Yeah, also I have like a state machine here, because if I paint the whole screen at once, it will take like 100 milliseconds or something. And now we can see how long that is. If I do, see here, 5 milliseconds per division, I have 5, 6, 7 or 8 milliseconds inside that paint screen loop, or a part of the loop. Yeah, so so if the timer has timed out, I reset the timer and paint the screen. I also switched state, so it has 4 states. That's what this means. And I set up the ADC to flip between the 2 ADCs that I have, depending on which state it's in. So yeah, so I don't mean that anyone is supposed to understand what this means, but yeah, so there you go. So, and here you can also see those values I had in my calculations. It's a bit different, 190 then divided by 10 or 19. It's because I have a fixed point decimal representation here, so yeah. So yeah, so you like that? I think I've explained everything about that. So, and I think it's time to move on and try buttons and stuff. So actually the timer was a bit difficult. I can show you how that works. Everything is from the datasheet. Like, I always have it up here in background. So just goes to, first I tried the timer 0 to get like 100 millisecond or 30 millisecond or some sequence or timing. There you go. So the problem with that one was the timer, or the peripheral clock, I/O clock, which is called here. It's really fast, and you can only divide by 1024 on that clock, so you don't get as long delay as you want if you want a delay or something timing out. But timer 1 is going up to, the prescaler is going much farther, the other one was just going up there. So you have these options. I'm currently here. You can see this is the old timer, this is new one. So I'm basically just setting the control register CS10, which means I'm setting these bits 1110, so that's divided by the 8192, as I said. So, and then you have the delay, so that is how long the counter counts from 0 up to this value, and when it gets there we get an interrupt flag, and I clear it, and the way to clear it is to set it. I have no idea why it's like that. It doesn't make sense at all. But anyway, so has timed out here, which basically checks if the interrupt flag for the timer, which is that output comparator for value A, which is that OCR1A, if that has been reached, we return yes, it has timed out. And if it has timed out, we reset the timer, and reset the timer means basically clearing that flag by setting it. Again, what the hell. And this is not a continuous toggle, continuous running mode, so you have to clear the counter also, which was really weird, because I thought in CTS mode that will clear by itself, but not this guy. So if you use that one, you have to use OCR1C, but OCR1C doesn't have a interrupt flag. So yeah. Well, if I get that loop to 50 Hz, then I'm sampling at 50 Hz. Right now I'm sampling at 100 kilohertz or something, which is much better. There's a lot of things I've been thinking about to make this work, especially that ADC on the left there. So yeah, that's overcurrent feature that I was really happy about, really. So the next thing I think I have to check now is that value down there, which is 19 or 18. And yeah, then basically need to load the thing. And this guy over here I'm going to use for testing the thing under load. So, but I need a heatsink for it yet. So I think this works rather well, like it does now. I'm happy about the progress also. I really want to get this thing out there now. I'm a bit tired of the project, to be honest. Yeah,